In today's video, we're going to continue doing the validity of arguments, but this time we're going to have a slightly different method of determining whether they're valid or not. So let me bring up an example that we've done so far. If the tank is empty, then I must fill it. So if the tank is empty, then I must fill it. The tank is empty. Therefore, I must fill the tank. So there's a few ways of seeing that this is a valid argument. But one, the tank is empty, and the first line specifically says, if the tank is empty, do this. And the response that we got was exactly to do that. So when you have that, that is a valid argument. Here the tank is empty, and it speaks of what to do when you have an empty tank. So it's completely valid, and then we did what we were supposed to do when we had an empty tank. So it's valid that way. Another way, we did the Euler diagrams. If we take a look at, let's see, we have tanks that, tanks that need filled. So that'll be the circle for tanks that need filled. Ours is an empty, as part of the empty tanks. So since ours is inside of the empty tank circle, we see that it is inside of the tanks that need filled as well. And so the statement is valid either way you look at it. But I'm showing next how to do it with a truth table. So the idea is this. If the tank is empty, then I must fill it. The tank is empty. Therefore, I must fill the tank. So, the way you do it is this. We're going to let P equal one of these things. Since we're going to do a truth table, I need P and Q. So P will be the tank is empty. You get your P and Q from the very first statement here. There's my P right there. And I must fill it is going to be my Q. So now let's take a look at the way our structure is. The first line of that is P implies Q. The tank is empty is a P. Therefore, then I must fill the tank is a Q. So this all breaks down in the following format. In the top part, I probably should take this off for a second because I don't want to do that just yet. But this top part up here is an AND statement. This is P implies Q and P. And of course down at the bottom is implies that. So let me get a bigger thing here. So what this is P implies Q and P, all of that implies Q. So we make a truth table out of it. As usual, since we have P and Q, we have to do 4 rows. And then we go as we normally do. Let me do P implies Q. Remember, these we've done a lot of these before. P implies Q. We had true, false, true, true. Now I have P implies Q and P. So this is only going to be true whenever both parts are true. So let's take a look here. True for this part, and true makes true. For the next row, true and false makes it false. And then for the last two, we have 2 falses. It doesn't matter what the other one is. These will end up being falses. And then all of that stuff, P implies Q and P implies Q. So now I am working on specifically this implication arrow here. So you remember, we're starting from this column and we are going to this column. So starting with this one, true implies true is true. Now I don't need to do anything else because false implies anything is true. So all of these are going to be true statements. And so what we have here is called a tautology. I have spoken of that before. But when you see that over there, that's a valid statement. So when you reach a tautology there at the end, you know that the statement is valid. That's how we check to see if these arguments are valid. We have to convert them to symbols first and then evaluate them almost numerically. If our guests arrive before lunch, we'll eat out. We ate out. Therefore, our guests arrived before lunch. Let's take a look at what we have. So I'm going to let P equal our guests arrive before lunch. And Q will be we'll eat out. So what's our structure? Well, the first part, it's always going to be structured like this. P implies Q. Now the next line is we ate out is a Q. Therefore, our guests arrived before lunch. This is a P. So the structure of this is P implies Q. This time we have and Q. That implies P. P, Q. Give yourself plenty of room when you're making this table because there may be a lot of pieces that you have to work on. So you'll always have this. In fact, you'll almost always have this as well because most questions are simply structured that way. So this was true, false, true, true. Then we'll go P implies Q and Q. Let me have my cursor if I can find it. There we go. So remember, this is only going to be true when both parts are true. So I have a true for this one and a true for this one next to it, the Q, so that's true. I see a false here, so I immediately make that false. I got true and true for the next one, and then finally false and true gives me a false. And we're almost done. Now let's set up the final thing that we need. We have P implies Q and Q implies P. So remember, we're starting before the implication arrow with this stuff. That means anywhere where this was a false to begin with, these are going to be true. Now let's take a look at here. We have true. True implies true. So that one's true. And then on this one here, true implies, let me go over to P, what is it? False. So that's a false. Once you see one false, the statement is invalid. In fact, you can stop the moment you get to a false. If I can avoid sweets, then I can avoid the dentist. I can't avoid the dentist. Therefore, I can't avoid sweets. So this one's structured a little bit different than the other ones. Here we'll still do what we do all the time. P will be the stuff before the comma. So that'll be I can avoid sweets. And then Q equals I can avoid the dentist. So the structure of our argument is like this. The first line is P implies Q as per usual. The second line though says I can't avoid the dentist. But Q is I can avoid the dentist. What we just did is we just have a squiggle Q, that's all. So a not Q is what goes into that spot. Similarly, I can't avoid sweets is not P. So this time our structure from all of this is the following. We have P implies Q and not Q implies not P. So let's go ahead and set this one up. P and Q. True, true, false, false. True, false, true, false. P implies Q. True, false, true, true. Now let's go ahead and get our squiggle Q, or not Q. That'll just change Q from true to false and vice versa. So I'll have false, true, true. Now, when I look at P implies Q and not Q, let's see what I have. So P implies Q, so true to false is, I'm sorry, I said it wrong. This is an and symbol, so I need both parts to be true for this to be true. So true and false is false. False and true is false. True and false is false. True and true is true. All right, let me get a column for squiggle P. So I'm going to undo whatever P was. And now I'm ready to stitch the whole thing together. So I have my P implies Q and squiggle Q implies squiggle P. Now the antecedent of this arrow is all of this stuff here. So if I go to the column for all of that, any place that this starts with false, these are automatically going to be true, because if false implies anything. Now for the last one, I'm starting here, so I have true, and I'm ending here, so true implies true. We know that that is true. So since we have a tautology here, the argument is valid. A mathematician is a device for turning coffee into theorems. You turn coffee into theorems. Therefore, you are a mathematician. Now, the structure of the first line is not in an if-then format. We can be helped with the if-then format by considering these: turning coffee into theorems and a mathematician. So let me see if I can use those phrases to rewrite this first line into a more of a if-then statement. So we have a mathematician as a device for turning coffee into theorems. So if you are a mathematician, then you turn coffee into theorems. So let's do that. If, so it's a rewrite. If you are a mathematician, then you turn coffee into theorems. You turn coffee into theorems. Therefore, you are a mathematician. So let's take a look at the structure now. If I have a P, I can set that to be you are a mathematician. My Q will be you turn coffee into theorems. The structure then that we have is the top line is P implies Q, as is almost always the case. You turn coffee into theorems, that is a Q. Therefore, you are a mathematician is a P. Let's take a look. P imply, well, I'm going to do my truth table first. So we'll do the P, true, true, false, false. Q, true, false, true, false. P implies Q, true, false, true, true. Then we have P implies Q, and, oh, actually I didn't write the structure today. This is P implies Q, and Q implies P. So let me do P implies Q and Q. So I'm going to have true, false, true, false. And then the last one puts everything together. We're going to have P implies Q and Q implies P. So since all this stuff is the antecedent, wherever it is false, I automatically have true statements here. Now let's take a look. True implies true, I'm implying P. True implies true. That's true. And then true implies false. We know that's false. So this is invalid. Mia kicks, or Drew passes. Drew does not pass. Therefore, Mia kicks. So here we have a different collection of things. P will be Mia kicks. Believe it or not, that is a complete sentence. Q is Drew passes. And so the structure that we have is on the top line, this time it is P or Q. The second line, Drew does not pass, is not Q. Therefore, Mia kicks P. So our structure is this: P or Q and not Q implies P. Let's go to the truth table. I got my P, Q, true, true, false, false, true, false, true, false. Now then, P or Q, as long as one of them is true, the whole thing is true. So I have, the only place I'm going to get a false is in the last line. Then I have P or Q. I keep going faster than I want to go. Let's do not Q first. So here I'll reverse all those Q's. Now I'll go ahead and put these together. P or Q and not Q. Remember, this is only going to be true in those places where both of these are true. So true, false, that'll be false. True, false, false. So I only have a true in one spot, but all the rest of these are false. And now the whole thing. P or Q and not Q implies P. So once again, all this stuff is the antecedent. So wherever I see these falses, since they're part of the antecedent, the whole statement here will be true in those. So now I just need to look at this true implies this true, which is good. All trues. So the statement is, or the whole thing is valid. Since all of our arguments break down to P's and Q's anyways, it makes sense to try a few of them that are structured like that just to begin with for practice purposes. So here I have P or not Q. P, therefore not Q. So the structure of this thing here is P or not Q, and P implies not Q. I think for the top, let's do a not Q first. Then let's go ahead and do P or not Q. So here, as long as one of them is true, the whole thing is true. So I have true for P, I have two trues to begin with. Then over here, a not Q, I have a true. But then on this line right here, I have this false, or false gives us false. Then I'll put that P or not Q and P. I already know this is going to be false. Now here, true, I know the first true P values are true, so these are going to be true. And the last one, I have a true here, but a false here. So that'll be false. Then as I'm putting it all together, P or not Q and P implies squiggle Q. Well, this is all part of the antecedent here. This is the antecedent column, so these falses will become trues. And then I'll take a look at the rest of these. True, remember I'm looking here at this column, the not Q column. So right here I have a true, implies a false is a false, and we can stop. We are already in an invalid statement, argument. Next, the structure is P implies squiggle Q, squiggle P, therefore squiggle Q. Let's go ahead and do the truth table. Let me get a squiggle Q. Let's do a squiggle P. Now the structure of this here, we have P implies squiggle Q and squiggle P implies squiggle Q. So basically I'm building that up. So my next line will be P implies squiggle Q. I think I'll just do that. You know, now that I think about it, I'm going to leave this in the video because I'm thinking about it as I do the problem. What I'm going to do here is I think I'm going to put a squiggle P here first. Actually, no, I'll take that. I'm going to do this. I'm going to do P implies squiggle Q first. So let's take a look at that. P implies squiggle Q. So anywhere that P was false first, these are going to be true. Now, true implies false is false, but true implies true is true. Now I'm going to do my squiggle P. Now I'll do P implies squiggle Q and squiggle P. This way they're right next to each other. I figure that's very nice as far as filling out this table. False and false is false, true and false is false, but the last two rows are true. So we have false, false, true, true. Finally then, my last piece here, I'm going to have P implies squiggle Q and squiggle P implies squiggle Q. So for this, my antecedent is in this column right here. Now my squiggle Q is all the way over here, so I got to keep that in mind. But the antecedent, wherever these falses are, I know I can put trues here. Now I just have to worry about true going to false. So here's a true, my antecedent true. Let's take a look at Q, or not Q. Right there is a false. True implies false is false, so I can stop right now. This is an invalid argument.